Hello, everyone. Welcome to Advanced Water Pollution Monitoring, co-sponsored by the Environmental Law Institute and the International Network for Environmental Compliance and Enforcement, or INECE. This webinar is made possible by funding from Environmental Governments Institute International with support from the Wasserman-Slatkin Family Charitable Donor Advised Fund. My name is Susanna Dibble, and I'm a staff attorney at the Environmental Law Institute and the managing director for INECE. INECE works to raise awareness for compliance and enforcement, develop networks for enforcement cooperation, and strengthen capacity to implement and enforce environmental requirements. You can find more about our work on our website, inece.org. For our webinar today, George Wyeth, the visiting scholar at ELI, will be our moderator. George previously spent 27 years at US EPA and a variety of roles as an attorney and as an internal advocate for innovative approaches to environmental protection. We also have an amazing group of speakers today. Thank you to Pablo, Anabela, Margaret, and Brittney for joining us to break down and discuss such a timely topic. Now, both following each individual presentation and at the end of all the presentations today, we'll be taking some audience questions. Please don't wait to submit any questions you have. You can use Zoom's Q&A function at any time throughout the webinar, and our moderator and speakers will be able to see it. We encourage you to use the chat for any observations and comments, but we will be pulling discussion questions from the Q&A box at the bottom of Zoom's interface, not the chat. Today's webinar will be recorded and posted on the event webpage to view later. So if you can't stay for the whole webinar today, the recording will be available within a few business days at eli.org. So thank you for joining us for this important issue. And now I'll turn it over to George.
Thanks, Susanna. Our first speaker comes to us from the Portuguese Environment Agency, Anabela Rebelo. She is the senior officer at the Department of Hydrologic Resource. And I'll just turn it over to her.
So, good morning, everybody. It's a pleasure to be here. Thank you for the invitation. I will just start sharing my screen. I hope you see it. Please let me know if that's okay.
Yes, we can see it.
Okay, thank you. So I work for the Portuguese Environment Agency, Water Resources Department, as George says, and for more than 25 years, I've been working as a water permit writer, and more currently as senior policy advisor, and working as an expert in several EU working groups. So I will speak about water pollution. So I will give you an introduction overview about the European legislation and how do we deal with monitoring in that way. So, So we have in Europe, so we have a huge, several group of legislation for protection the water. That interlinks with the drinking water, groundwater, major accidents legislation, industrial emissions legislation, with the same contribute to the main framework, which is the Water Framework Directive, with a main goal. And the main goal is to achieve the good water status, which means that for example, for surface waters, good ecological and good chemical status, to ensure that preventing deterioration and protecting the improving water ecosystems. One thing that applies in this legislation, and it's very important for us to achieve the status, is the appliance of the principle one out, all out, which means one monitoring data bad, the status will fail. That's why monitoring is so important in our legislation. So for surface waters, like I said, we have the ecological status, which is given by general and chemical and physical-chemical parameters like OD, nutrients, pH, specific pollutants, persistent and bioaccumulative and toxic substances that are relevant at regional or national level, but not a problem at the EU level, hydromorphological quality elements. And for the chemical status, we have specific chemical substances, usually known as priority substances, which are a problem at the EU level, so a problem at the European Union-wide level. And only so like I said, so the status is given by the worst of the two status, and below good, everything will fail. So one monitoring data bad, all the status will fail. So for the priority substances, we have a long list, up to now 45 substances, synthetic substances, pesticides, namely synthetic and pesticide substances, organo solvents, and so on. And this kind of list is currently under review, and in a short time it will include pharmaceuticals, cosmetic, so daycare products and substances, and also hormones. So hazardous priority substances means that member states must reduce, in 20 years after classification, must reduce emissions, discharges, and losses. Priority hazardous means that member states needs to phase out all discharges, emissions, and losses of those substances. But how do we find the substances for this list? So one of the process, and one thing that was noticed, namely for this last revision that is now in the end, that monitoring was lacking. So there was this lack of good monitoring data, namely in the compounds of emerging concern. For that, it was created for the purpose of to determine the risk of substances posed to surface waters. It was created the mechanism of watch list. The watch list is a large monitoring program all over the Union, the European Union, to obtain high quality data on specific pollutants, and it's reviewed every 2 years. And depending on the results, some substances go to the prioritization process, and for that it will be applied environmental, so the derived and applied environmental quality standards. So this list, as it was created with 225 monitoring points all across EU, 8 points in Portugal. It's supported by the Joint Research Center, which is the scientific arm of the European Commission. So all monitoring methodologies and all the sampling procedures are according specific and harmonized standards. Also, all the data are collected in the same way and comparable, and for that they are comparable. So the first watch list was proposed in 2015, and then each 2 years, 3 years, it was updated. Some substances were removed from the first watch list, like as you can see, for example, diclofenac. But what that means that for two things. In one way, there was already enough data to classify that substance and send it to the prioritization process, or the data was enough to consider that the substance was not a problem, and therefore it was removed, and other ones were added. So first watch list in 2015, second in 2018, the third in 2020. In 22, we had the fourth watch list, and as you can see, the number of pharmaceuticals and hormones were increasing. And the fifth watch list from this year. So despite the new priority substance is already basically almost finished and will be published soon, the process of watch list will continue, and now this is the new list of substances, and in 2-3 years it will be reviewed again. So the new list of substances includes the previous 45. From the previous 45, some substances that are historical historical pollutants, and for that it's no longer possible. So there are no registers of emissions. So it's not possible to take actions from the discharge side, from the human side. So what we only need to do now is monitor to evaluate trends and to ensure that try to ensure that the pollution will decrease. So try to understand how it will be the natural behavior of these substances in environment, like for example atrazine and other historic pesticides. Other ones were remained in the list, and a few ones more were added. And I'm going just to go through this, and I will show you now the new ones. And the new ones, as you can see, will be more. So it will be more hormones, like the 17 beta estradiol, and pharmaceuticals like azithromycin, also some metabolites of specific pesticides, so the plastics like the bisphenol A, but a huge effort on the compounds of emerging concern, namely from pharmaceutical or daycare used substances, like, for example, the triclosan, but also pesticides, like, for example, the glyphosate, which is also a new substances. So for these substances, environmental quality standards are applied, and I'm just going to return a little bit previously to show you that environmental quality standards can be applied to inland surface waters and other surface waters, like coastal waters, and as an annual average, AA, or a maximum allowed concentration. So the maximum peak that can be applied to that kind of substance. Also, when applicable, it was developed environmental quality standard for biota, and some substances were identified that tends to accumulate in sediments and or biota. So all of that work is done, and it's going to be published soon. And then member states need to monitor surface waters with these kind of substances. And if one monitoring point is out, all the status will fail. So these substances are, they contribute for the evaluation of chemical status in parallel with the ecological status. So how do we, from the point of discharges, we evaluate this kind of substances from? So when we have a permit, when we have an industry, when we have an urban wastewater treatment plant, and we have to evaluate the discharge, we will basically try to find a combined approach. So we will look from the treatment plant, what is the best available technology, what would be taking into account the performance of the technology, what would be the minimum concentration that can be discharged. So minimum in terms of value, okay? So the lowest value, possible value that that is possible to achieve with the available technology. On the other hand, we have to look from the water body perspective, what is the maximum concentration that the water body can receive. In that way, we have to combine these kind of two approaches based on a risk assessment approach and define specific emission limit values for this kind of substances and to put in our permits. And not all it was not always like that. So even with this principle divided on the Water Framework Directive, we noticed that in when we looked at the industrial emissions directive, so the legislation for industries and the legislation for the water bodies, something was missing. And under IMPEL is the European Network for the Implementation and Enforcement of Environmental Law, we noticed that there was some kind of gap between these two directives. So under this project, Integrated Water Approach, we defined a checklist for permit writers, and with the application of that checklist to a case study, it was possible to identify a clear gap in the Industrial Emissions Directive connected with the WFD. And in the revision of that directive, a specific article was put it there just with the conclusions of this project of IMPEL. That's also the importance of working in network. The new Urban Wastewater Treatment Directive was just revised and published last year, in the end of last year. It applies to agglomerations, so to urban areas, and so all urban areas must be collected and have at least a minimum secondary treatment. Whenever the discharge is in areas of risk of eutrophication, it's mandatory to have tertiary treatment, removal of nitrogen and or phosphorus. A new head to this directive was the removal of micropollutants. So under now the new directive, member states will have to implement quaternary treatment, so phased on time. So from 2033 to 2045, we will have to implement for all the biggest plants, so above 150,000 population equivalent, we will have to implement quaternary treatment, so removal of micropollutants, and from 10,000 to 150,000 population equivalent agglomerations with this kind of loads, we will have to develop a risk assessment to understand if there's a risk of accumulation of micropollutants in the receiving water bodies, and if yes, all of these plants will have to also upgraded with quaternary treatment. And the quaternary treatment is the removal, at least we have to prove the removal of 80% of six indicator substances from category 1 and category 2. So as you can see, these kind of substances are in the majority pharmaceuticals, so they are just indicators of the performance of the treatment, we will have to, like I said, to define these risk assessment areas. So for the areas where we have the risk of accumulation of micropollutants. So as you can see, so this is a copy of the Swiss legislation of from Switzerland, and as you can imagine, now we have to improve our monitoring capacity in this kind of substances. We also another new thing in this directive is the wastewater surveillance. So we will have to create a national system for cooperation and coordination between health and environmental authorities to establish surveillance on emerging pathogens, like emergent health parameters, like, for example, SARS-CoV-2, polio, influenza. So we will not control health infection, okay, on population. We'll try to understand what is going on wastewater. So what is the trend of this? So if we can find trends through wastewater, that we can give some information for public health authorities. So we will also need to monitor, it will be also mandatory to monitor antimicrobial resistance. And because it's not easy and there is not exactly yet a standardized procedure for monitoring, the European Union, and to ensure that all member states will do it on the same way, will develop a legal act with standardized and common procedures for monitoring for antimicrobial resistance. Also regarding another mandatory stuff that we have to, so another mandatory requirements that we are obliged. So despite the typical parameters, BOD, COD, TSS, we'll also have to, for tertiary treatment, nitrogen and phosphorus. For the quaternary treatment, the 6 indicator substances. For water reuse, when derogation, there's a possible derogation for nutrients if we have reuse for agriculture. In that way, we'll have to comply with monitoring on nutrients, not only on the water, on the wastewater, but also on the irrigation waters and in the crops and soils. Pollutants that are likely to be found in urban wastewaters, like the priority substances or the specific pollutants, or the pollutants under the groundwater directive. The pollutants that are also listed in the pollutant release and transfer register. This is another obligation that we have to taking into account the use of chemical substances at industrial sites, pollutants from the sludge directive, pollutants from the drinking water directive, and also PFAS, and not here, but it will also be mandatory, microplastics. So we have to monitor sludge pollutants in sludge, also greenhouse gases, energy, because this is also mandatory that treatment plants must be neutral from energy neutral, and storm waters and overflows, and also urban runoffs from separate systems. So according to monitoring requirements that we have so far, and to ensure that in the Water Framework Directive, all data are comparable among member states, there is not a list of standard methods, but there is a directive that establishes technical specifications for chemical analysis, which means that specifies the quality requirements for the monitoring methodologies, monitoring and sampling methodologies. For new parameters, microplastics, micropollutants, and antimicrobial resistance, there's this development of legal acts, so binding rules for member states, and for that working groups are being established in combination with the Joint Research Center. So this is the support, it's the support, the scientific support of the European Commission, and we are all working on that. So techniques, what we know so far that for this kind of these new substances, for these new requirements may differ from matrix to matrix. So from sludge and wastewater, so the methodologies could be different. Or soils, for example. In terms of analytical procedures, may differ according the aim. For example, in microplastics, if we want to measure the size, if we want to measure the shape or mass, so it will be applied. So different methodologies can be applied. Or for example, on the antimicrobial resistance, if we want to do environmental surveillance, we can look, for example, on non-cultivated base methods. So we can look at that material. But if we wanted to look, for example, on health monitoring, on infection, on population, we must look only on cultivated methods because we need to look at live material. There's this kind of, so in terms of these legal hats that are being prepared in the by the European Commission to harmonize these procedures, there is the preference for to use what is already being developed or already being published in the SS standards, so ISO, SAN, or even the American standards, and all data, data is reported according to the through the European Environment Agency to ensure transparency.
Excuse me,
I'm
Anabela,
finishing.
I'm sorry. Okay, thank you. Oh, great.
It's my final one. Effective monitoring ensures compliance with EU environmental legislation, namely in European-wide water protection framework, monitoring central in major policies in Europe. The European Environment Agency collects, validates, and publishes all environmental data, enabling transparency and accountability. Harmonized standards allow comparable data across all member states, and platforms like the Water Information System for Europe centralize and standardize data for policymakers, scientists, and for the public in general, ensuring once again the transparency. So thank you very much for your attention, and I leave you with a picture from my Portugal, from Douro Valley, where port wine is produced. Thank you very much.
Well, thank you so much, Anabela. What we're going to do with questions is we will take one or two questions specific to each presentation and then reserve time. We were going to try to reserve a good bit of time at the end for a more overarching discussion. And again, please use the Q&A function to raise your questions. So we have one question specifically for you, Anabela. The Lake Stewards of Maine have asked, within the risk framework, how are you evaluating compounding effects or synergy between chemicals? So we have multiple chemicals in the water. How does that affect the risk analysis?
Okay, for the risk assessment, we will have, so it's also being developed by the European Commission, a methodology. So far it's not yet set. Regarding the synergies among chemicals, we will evaluate, so the new priority substances, the new list for priority, the revision of the directive of priority substance as specifications for the monitoring, for the monitoring of combined effects. So there will be specifications under that directive, and of course we will have to use that kind of specifications. I'm sorry, I'm not so within what is written there, but I know that is written there something like to that. So we have to look at that, and we will have to use that kind of monitoring to evaluate the synergies. But is already. So you can try to find out. So the directive will be published soon. So when available, it will be public, and it will be explicit there how we can, how we must apply the combined effect monitoring, and to use that in the risk assessment, of course.
Great, thank you. And again, we're asking people to put their questions in the Q&A, not in the chat, just so we can make sure we're picking up all the questions. Our next speaker, moving on, is Pablo Aguirre, who comes from Chile, and he is the head of environmental intelligence, I love that title, at the Environmental Enforcement and Compliance Agency. Welcome, Pablo.
Thank you. Can you confirm that I'm sharing my screen, please?
Yes, you are.
Perfect. Thank you. Well, good morning or well, good afternoon, depending on where you're joining from. Thank you very much for the invitation to participate in this webinar. As George was saying, my name is Pablo Aguirre, and I work at Chile's Environmental Enforcement and Compliance Agency, the Superintendents of the Environment, or SMA. And I work specifically at the Department of Technology, Monitoring, and Information. But today, I come in representation of SMA to share with you how we are using different kinds of water-related monitoring data in Chile and how that connects to compliance and enforcement decisions. I'll start with a bit of context about who we are and the challenges we face. Then I'll talk about an illustrative case of a fragile aquatic ecosystem that show us how technology can complement other actions to enforce law. And finally, I'll describe some of the technology-based tools and approaches we are developing to move towards more preventive and risk-based enforcement. All right, so what is SMA? So to start, SMA was created 15 years ago as the Environmental Enforcement Authority here in Chile, and we are responsible for monitoring and enforcing a wide range of instruments, emission standards for different environmental components such as air and water, among others, also environmental permits, prevention and decontamination plans, and other environmental regulations across the whole country. In practice, that means that we supervise more than 20,000 regulated facilities spread along a very long and diverse territory that is our country. That's from large mining projects in the north to agricultural activities here in the center where I'm located, to salmon farms, also on forestry activities in the south, plus many, many other activities in between. And we also deal with very different types of obligations. Some are fairly classical, if you want to say it, emission limits, for example, for industrial wastewater discharge to rivers, groundwaters, or to the sea. And also other obligations that are very site-specific conditions written into environmental permits. So the combination is that we have many facilities, many regulations, and a very large territory. So given that reality, it is very, very hard to rely only on traditional side-by-side approaches. Therefore, we see in monitoring system and technology an important way to help us see where the problems are, how serious they are, and where also our limited enforcement resources can have the biggest impact. All right. A simplified but useful way of thinking how we work here in SMA is to think of all of our processes as a kind of chain. At the beginning of the chain, we have different signals. For example, periodic monitoring reports submitted by companies, data coming from sensors and other systems. Also citizen complaints, which in our case, most come from an online platform we have developed. And all those signals can inform investigations and potential inspections. And based on what we see, we might open formal enforcement case, negotiate a compliance program, or sometimes close the issue if the situations are resolved. In the case there's sanctions, there can be a range of actions from warning letters to fines, and in extreme situations, even the closure of operations or parts of this. Also, in the event of disputes, cases are reviewed by courts, which can take a very close look at the evidence and reasoning we have built. And in the case of SMA, we seek to have every step of this chain being supported by technology and information, which in this case is exemplified in these icons by different systems that we have been building in-house to support the different teams and also for regulated entities and citizens to report information to us. All that being said, let me now bring this closer to the subject of the webinar we are talking today by talking about a particular aquatic ecosystem such as wetlands. So in Chile, Chile has a very diverse set of wetlands from coastal marshes and peatlands in the south to saline lakes and high Andean wetlands in the north. And many of these are very important for biodiversity, for migratory birds, also for local communities, and also for regulating water in this, for example, in the north for these very dry landscapes. And these ecosystems are also very highly sensitive to changes in water availability. Groundwater extraction, for example, or surface water diversions, infrastructure and industrial activities can alter the hydrological balance and also lead to the degradation or loss of these wetlands and lagoons. Now, in many cases, these changes in this kind of ecosystems is gradual. Vegetation tends to dry out slowly, but the water table declines a little bit each year, and only after maybe extended periods of time, it might be possible to see if the damage become obvious. And that for an enforcement agency like SMA, this is a very challenging setting. Because in cases like this, we are not just asking, for example, if a pipe is exceeding a certain level of concentration limit or a particular day, but rather we are asking if an ecosystem is becoming degraded over time. And if so, if that can be linked or is linked to a human activity that we have to supervise. Of course, answering that requires long-term analysis and careful interpretation of the analysis that we perform. Over the years, we have had enforcement cases related to this kind of ecosystem, to high Andean wetland systems, showing signs of significant degradation associated with human pressures, such as, for example, groundwater extraction from industrial projects. And in those cases, to build an enforcement case, we have had to combine different kinds of information, such as hydrological data, including time series of pumping rates and groundwater levels in monitoring wells, also field observations, documenting the loss of wetlands areas and the changes in vegetation, and also spatial analysis using, for example, satellite imagery. This particular set of information, satellite images, allow us to see these long-term patterns of drying, changes in otherwise natural trends, and to compare also different parts of the same basin, and to link eventually this to the location of industrial activities and other pressures that could be happening in the territories. For cases like this, courts have examined also our evidence in great detail. For example, looking at the quality of the data, the methods we have used, and how we have argued causality between extraction and environmental damage. These early experiences we had show us that advanced monitoring, the use of advanced monitoring data can be accepted and can support very strong enforcement measures, but only, and this is very important, only if our methods, our quality assurance procedures, and our documentation are solid and transparent. At the same time, cases like this also bring harder lessons that even when enforcement can be successful in legal terms and be defendable at courts, if we act too late, the ecosystem may already be irreversible damage. So these kind of experiences also had led us to the conviction of investing more effort in the strategic use of monitoring and technology, seeking not only to reconstruct damage after the fact, but rather to detect early signals of risk and also support more preventive enforcement.
Excuse me, Lee Paddock, your hand is up. Did you want to ask a question now or ask later?
I meant to be up. Sorry.
Okay.
No worries.
Go ahead,
All
Pablo.
right. Okay. Right. So this figure tried to illustrate somehow what's our current perspective on the use of technology and information. And this is across different areas, not only for wetlands or water monitoring. We see technology as a way to first extend our territorial reach, right? Try to cover more territory so we can see beyond the few sites that we can visit in person. Also to generate alerts when thresholds are exceeded, rather than just waiting for example, for annual or regulatory reports. Also to eventually monitor new variables that were previously very difficult to do or even impossible to observe. Also to better understand complex systems like maybe entire basins, wetland complexes, or networks of discharging pipes. And also to automate routine processes. And this is very important because we want human time to be devoted to interpreting maybe information and making decisions and not and try to minimize the time of wrangling data and dealing with those kind of details. And at the end, the key point is that technology is not an end by itself. And that's very important. And me coming from a technology area, this is something I like to highlight frequently. Technology is not an end by itself. So we are not trying to maximize the number of sensors or the number of dashboards, but what we want is better decisions and better actions. Decisions that are more timely, that are better targeted, that are more proportionate to the risk and impact, and so on. Ultimately, what we want is to modify incentives of the activities that are generating the pressure on the conservation objects, on the ecosystem, and also on human health. That's overall the vision that we have regarding technology. Now, diving into some of the current lines we have for related to monitoring, to water monitoring. First, let me give you a concrete example on the more quotation mark classical side of water pollution, such as industrial wastewater discharges. In Chile, discharges of industrial liquid wastes to surface water are regulated by emission standards that specify limits and monitoring obligations for flow and also for a range of water quality parameters. And facilities must monitor and report their results periodically to SMA. And for many years, data was reviewed more or less manually with a certain level of automation coming from legacy systems that were created before SMA existed. That meant that in some cases, problem detection could occur months after the fact. And it was also very difficult to have a more aggregated, maybe a national picture of how different group of discharging points were performing. And to address this, we have incrementally been improving the legacy system over the years. And we have now come to the point of relaunching very recently a modernized online reporting platform for industrial wastewater, a system we call CISREL. And through this platform, regulated facilities can submit their monitoring data electronically in a standard format and can analyze all the information they have submitted in a clear and user-friendly manner. And on our side, as SMA, we can also automatically evaluate each report, checking whether it was submitted on time, whether all mandatory variables are present, and whether the emission limits have been exceeded or not. Also, teams can use a set of tools to manage and analyze the submitted information. And also building on the automated capacities of these kind of systems, we have implemented, for example, automatic tailored notifications. And with this, I mean that every month, 100 facilities receive an email summarizing how they did on each reporting obligation. For example, did they report on time? Did they report all the required parameters? Did they exceed any limit? And so on. And this has been on production for a couple of years. And seeking to understand also if these actions, these emails, have had any impact on regulated entities. We recently evaluated this intervention using a quasi-experimental method, and we found that these very simple emails, basically giving better feedback based on the data we already had, significantly improved the timeliness and completeness of reporting. And this is, for us, a very good example of how a relatively modest technological change can strengthen administrative compliance and also give us a much more reliable basis for further enforcement and analysis. Well, of course, not all of our water-related challenges are about individual discharges. We also need to understand what is happening in ecosystem and sensitive sectors that affect water bodies. And here we're working on different fronts. First, for many projects, for many environmental permits, we require and standardized environmental follow-up reports for the water component. And these reports specify which variables must be monitored at which location and at which frequency. And given that we have a reporting format that is standardized for all of these facilities, we can eventually integrate this data and look at trends not only across time for particular facilities, but only, for particular sectors, but also across projects within the same basin. Second, also for certain particular sectors, we have introduced online sensors and real-time or near real-time reporting. This includes, for example, monitoring networks around tailing dams, sensor systems in projects located in salt lakes, and also water quality sensor for salmon farms. In these cases, data such as levels, flows, different quality parameters are transmitted automatically to SMA, and in some cases also checked against the predefined threshold or patterns. And also, in addition to looking at the values of the measurement itself, like the actual measurement of the parameter, we are also monitoring the health of the data stream. That is, for facilities that must report at a given frequency to us, we have implemented disconnection alerts, where every week we check whether they have sent the data as required. And if a facility stops reporting or the frequency drops, the systems flag this and generates an alert email. And since we introduced these disconnection alerts, we have seen a clear improvement in connectivity and data completeness from our online sensors. And it also means that we are gradually building a database of reporting gaps over time, which eventually could be used, for example, by inspectors and lawyers. For example, we could eventually analyze if repeated or strategic disconnections can be interpreted as a pattern of non-compliance and not just as random technical glitches or problems. A third line, and also going back to wetlands, we have developed in-house tools that use satellite imagery to monitor wetlands extent and vegetation conditions over large areas and periods of time. We can now monitor water and vegetation using decades of image for almost all wetlands in the country. And together, all of these elements that I'm mentioning help us move from a world where we only see maybe a few discharge points in the time, a few events in time, to one where we have a more layered and also spatially explicit view of pressures and also states in water bodies and water-dependent ecosystem. And the idea of all of these lines of work, of course, is not to replace the field work, which is essential and key for any enforcement agency, but to have consistent and frequent layers of data that can help us flag areas or particular facilities where there could be potential impacts or non-compliance issues, so we can investigate further those. Now, despite all these advances, we are also very aware that we still have a long way to go. And for example, one major challenge is the institutional capacity, given that we are receiving this large amount of data, this continuous data stream in some cases, also large files, such as satellite imagery and so on. And this requires robust data management and infrastructure, quality assurance, procedures, and also teams that can interpret these results. Without that, it is very, very easy to end up literally drowning into all of this data instead of being guided by the information that we can create through the use of this data. Also, a second challenge is the legal robustness and trust. That is when we base enforcement action on sensor data, technology, satellites, etc. We need to be able to show to teams in SMA, in our institution, to courts, and to the public that our data is reliable, that our methods are robust, and that we understand their limitation. That means creating clear protocols of how we manage data, create audit trails, transparency also about how we process and use the information. And also a third challenge is to strengthen the collaboration with internal teams here in SMA, as well as other agency and other actors, so that data not only supports enforcement, but also prevention and shared understanding of what it is in this case. But there is also opportunities that the use of analytics and also AI brings, with thousands of time series and spatial layers, machine learning tools, and so on. All of these can help us detect patterns and anomalies that humans may miss, and can help us prioritize also inspection or simulate scenarios. But we believe that decisions with legal consequences must always remain under human responsibility. That's also very important. and that any model that we use or we create need to be also explainable and auditable. And finally, a more general lesson from the wastewater example I told you before is the idea of dedicating time to evaluate our actions. We need to create a culture evaluation, and we think that is important as an enforcement agency because that forces us to be honest about what works and what has no effect, where we might need to redesign our action and stuff like that. It also helps us to justify further investment in things like monitoring and technology, for example. And this is the last slide. To conclude, I would like to dedicate 1 minute to this figure. Here at SMA, we are now very explicitly trying to follow a responsive enforcement approach. That means that we have a ladder of possible responses from very soft to very strong, and we try to match, or the idea is to match our responses to the seriousness of the behavior and the risk. And at the lower end of the ladder, we have preventive alerts and complaints reports that are triggered by monitoring signals that we were mentioning before. In the middle, we have information requirements, warning letters, permitting requests in the context of formal inspection. And at the top, and in cases of serious or irreversible environmental damage, we can impose eventually substantial fines or even closure of facilities or parts of it. The idea is that all the monitoring and technology I have described today and more is valuable only if that help us to move along that ladder in a timely and proportional way. And in that context, at SMA, we have been working on a series of sector-specific strategies. So far, we have 2 that we have published in our website that translate this responsive enforcement approach into particular activities and objectives. And finally, the idea of all of this is that the goal is not necessarily the punishment for its own sake, but to change behavior, to reduce risk, and to protect the ecosystems and the communities that also rely on them. So our ambition is to move more gradually, or not, from a reactive model to a model where advanced monitoring is one of the tools that can help us to see problems earlier, act at a lower cost, and also strengthen the credibility of environmental regulation. And with that, I'll finish. Thank you very much, and I look forward to the discussion and questions you might have.
Thank you, Pablo. That was really fascinating. Again, we'll just take 1 or 2 questions specifically on this presentation, and then reserve time at the end for a more overarching discussion. We have 1 question. We have a couple, but I'll pick one here for you, Pablo. That is Chile finding major gaps with their regulated community. It seems that this is creating a gotcha culture instead of fostering cooperative relationships with the regulated community. So this is not about monitoring per se, but about the overall relationship with the regulated community and what your strategy is for that.
That's a great point. Well, I guess for time I didn't mention it, but one of the lines, of course, that we have as an enforcement agency is all the workshops and also like the, how we call it, the assistance to compliance measurements we do with the regulated entities to have like again, I guess like my message at the end was we are not seeking punishment, but rather seeking a culture of or an environment of tending to compliance. So we have a strong lines on that on assistance to compliance and the workshop we do also to make our regulation more accessible to facilities. And if I can tell you one example, I mentioned these sensor alerts we're sending weekly, so telling facilities, for example, if they are not sending their required frequencies. In that case, we have received many requests from facilities to meet with us to have further information about these actions that we are doing, and we have had a very positive reaction from the regulated entities. Like they appreciate also the process information that we can provide to them in for example, in these kinds of alerts, or also in the case of industrial wastewater that was mentioned, these monthly reports. We have had a good response from the regulated facilities. So I will say again, that's the point. The point of, for example, all these alerts that we create is that facilities are aware that not only that we are looking at them, but also that of how we are analyzing the data so they can tend to comply with the environmental regulation.
Well, great. Thank you, Pablo. That's a really interesting point that advanced monitoring isn't just a technical or enforcement tool, but it can actually be a sort of a quick feedback loop that can change the nature of the relationship. That's really fascinating. Thank you so much. Our next speaker is Margaret Sexton, who is the Director of Innovation Systems and Intelligence from the New South Wales Department of Natural Resources Access Regulator in Australia. And I'll turn it over to you, Margaret. Welcome.
Thank you very much. Have I got audio and video playing?
Yes, all good.
You're seeing it.
Excellent, thank you. Thanks to Susanna and INECE, and warm greetings to my fellow presenters and delegates here today. Good to see a couple of hundred of you online there. My name is Margaret Sexton. I'm from Australia, as you just heard. My presentation's slightly different. There are a lot of similarities with Pablo's work in Chile. However, we're a regulator for water take monitoring in New South Wales in Australia. And I'm going to be focused on how we use technology in the water monitoring process and how we integrate that to bring greater power to our intelligence. So I'm Director Innovation Systems and Intelligence and lead 4 main functions: the spatial and data analytics function, the information technology, operational technology, which is the tools used out in the field, and our intelligence function, which is future state scanning and setting up our regulatory priorities for the agency. And I'll just quickly acknowledge my team for their incredible skills, Ivars Reinfelds and Nick Milton and their teams. Is that moving on? No. There we go. So I'll give just the agenda I'll go through. I'll talk about who we are and what we regulate, how we use spatial monitoring to identify risks, how we combine observed data with other environmental information, and then how we use technology to gather evidence to support enforcement action. And I'll provide some case examples. So that last point is really about the so what for us. And it's not all about high-end enforcement action, of course, but there's some good examples that we can show about the impact that technology is having in our field of work. Seems a bit slow, I'm sorry. It is, maybe I can blame the time. It's nearly 2 a.m. here in Sydney. So who is NRAR? First, Natural Resources Access Regulator. We're an independent water regulator in the Australian state of New South Wales, and we ensure the lawful use of water so that everyone gets a fair share and its use is sustainable for communities, the environment and industry. We're 7 years old, so we were created in 2018 to deliver effective, efficient, transparent and accountable enforcement of water laws and to maintain public confidence in the enforcement of those laws. And those requirements are built into our legislation. So we're held to that standard in everything that we do, which is how we approach our use of technology. Before our agency, rules were often broken and the environment and the community and other water users really suffered. So we've worked really hard to change attitudes and, like Pablo, very much on the behaviour change aspect of things rather than wielding the big stick when it's all a little too late. And so we've developed more and more accurate ways to monitor compliance. Just in terms of context, I don't know how many of you are familiar with New South Wales, but we monitor, audit and regulate water take across a pretty wide and complex area. It's roughly 800,000 square kilometres of land, and there are more than 38,000 water access licenses. So those couple of factors alone mean it's quite a challenging task. Well, like everyone here, probably we use a range of technology and tools in our work, from remote sensing and GIS, which allows us to scan those vast areas from the desktop, to drones, which help us give an overview or get an overview of a property and access difficult to reach sites and provide high resolution images on the spot, which is quite powerful when dealing with landholders. And we have highly accurate survey equipment for determining depth, shape and volume of dams. And when potential non-compliance is detected using those remote methods, we often deploy our field technology to collect very detailed and site-specific information. So I'll just move on to then how do we use technology to identify risks. So for those, most of you are in the US, we use Landsat satellite imagery, the image there at the left. We use Sentinel from the European Space Agency. We use Nearmap, which is an Australian aerial tech company, so private, super high resolution aerial photo imagery. And we use Planet satellites, so near daily, and enables that specific tasking if we've got a job of work we'd like them to look at. So using technology is all very well, but with the complexity, we needed to come up with a method to structure it. So how are we going to systematically monitor for risk? So we've developed a framework based on timing, volume, location, and infrastructure. So we use remote sensing to detect if water take at a per license, per approval, and per property level is compliant with the timing of permissible take. So there are times when water is not allowed to be taken, such as during protected environmental water releases. And so we use satellites to monitor the environmental flow as it makes its way down the river. Volume of permissible take, so do dam inflow volumes exceed metered water take volumes? So we're comparing the metered versus satellite-based estimates. The location of the permissible use, so is water being used on a property that doesn't have an appropriate license or approval? And we might use false colour satellite or water to detect water content changes. And then infrastructure. Does the pump have an approved meter installed to measure and account for water taken? And we match the satellite observed pump locations with the metered take that we can access through the systems. So just show you some of what those look like. So the next few slides have some of those images for applying the framework. So these two Sentinel images are answering the question of timing. So they were captured over about a month around the time of an environmental water release event when water take was not permitted. So if you look from left to right, top to bottom, you can see the dams filling up over time, water showing there as the dark blue. So this is a time when water take is not permitted. Here's an example where we're examining volume. So we've done a bathymetric, bathymetric survey using surface area from our drones and depth from castable sounders. So they're simple fish finders that we're using very effectively in the field. And the graph on the right is a storage volume time series analysis, which was developed using Planet images of the water surface areas. And we convert the surface area to volume estimates using particular calculation methods. Here's quite a different look at volume. So it uses false colour satellite imagery, which shows healthy cotton crops in the bright red. And we compared crop water use estimations against reported use for a defined area. So understanding how much water crops need helps us flag properties that are reporting perhaps unusually low volumes of water for the area and the type of crop being grown. So the example on the screen at the bottom reported water use of 4.4 megalitres of water per hectare of cotton grown, whereas their neighbour to the top left reported 9.1 megalitres per hectare for the same crop. So we flagged this for on-site investigation, and it resulted in a successful prosecution for knowingly taking water while the metering equipment wasn't working, and there was a $375,000 fine on that one. Sorry, we've moved on. I apologise. This is location. We're looking at location here. So if you move from left to right, you'll see different images from pre-construction of a dam to the start of works, and then to a dam that is actually storing water. So this is, the question being, did the landholder have the relevant approvals to do the constructions and capture water? And this is location. So, oh gosh, it's very good. Determining if work's done on the property had the appropriate approvals. We've used LiDAR imagery to identify waterfront land, because there are particular rules about doing works on waterfront land. The map on the right is a cross-sectional map and an interpretation of the location of the river, the canals, and the floodplain. Here is an image. I think I've just got to be a little bit patient with that, because it seems to change slowly. Here is an application of infrastructure. So this is from drone imagery, and we took this closer look using drones because our broad-scale satellite screening flagged something suspicious in this area. So we deployed the field teams to go and have a better look. Right, so combining our observed data with other environmental information. In this section, I'll just talk through how we do that to make monitoring easier, make it faster and more accurate assessment, and identify trends. So we pull the pieces together using technology and smarts. We've got some very clever people in the team. So we use a combination of internally generated and observed data and intelligence, along with partner agency data. We're actually dependent on quite a significant amount of very important data from partner agencies, so it doesn't sit within our regulator, and then open source data and information from perhaps paid subscriptions and private tools. So we've used internal expertise to develop real-time and near real-time monitoring dashboards which draw on those various sources. I'll talk you through a case study. This is permanent planting. So for those of you the uninitiated, permanent plantings are crops that are sown or planted once and then occupy the land for multiple years, so they don't require replanting after harvest. Typically perennial trees, bushes or vines, fruit trees, nut trees, vineyards, berry plantations, and so forth. So the reason we looked at permanent plantings is because we noticed an increase in permanent plantings in a particular region where the water supply is particularly limited. So in both the rate of supply during hot weather and peak demand, and also the total available volume during droughts. So these factors present the potential to run for landholders to run short of water for large-scale permanent plantings that rely on general security, or where water users are relying on water trading to irrigate their crops. And so those together pose a risk of illegal water take when allocations are reduced. You know, people might be weighing up the cost of water theft versus the cost of losing an entire plantation. So obviously, economics, as water availability decreases, competition and cost increases. This is the sunrise crop mapping. So one of the other we purchased some crop mapping software, so we could get a picture of what crops are growing, where, and how they're being irrigated. So in this image, citrus trees are shown in yellow. The green is indicating grapevines, and in the blue you'll see nut trees. It's really very, very handy software for us in our work. Just trying to get to the next slide. Okay, here we go. Unlike annual crops, which can be withheld in dry times, permanent plantings need consistent moisture to thrive. So in general, mixed cropping with seasonal crops is a lower water risk, and permanent planting monocrops are a higher water risk. So in the multicoloured section at the top of the screen, mixed cropping, but in the blue at the bottom poses a particular risk because this is monocrop permanent plantings. So we're keeping an eye on this area. I'll just quickly skip to the next slide, which is just an example of mixed cropping. And then we did some spatial analysis and risk prioritization. So we compared estimates of water needed to grow the crop with the water entitlement the landholder had, whether they'd done any trades, and what they'd actually recorded in terms of their use. And we then ran a future water availability risk assessment, so prioritising the largest areas of the most water demanding crops with the least amount of water entitlement volume and historically the lowest reported water use. So from this, we're able to identify properties at risk of potential unlawful take, and we risk ranked those, provided the maps, and sent them to our field teams to go and inspect. So here's an example. One of the properties we looked at is an almond plantation, monocrop, permanent planting in blue, uses drip irrigation. It's 800 hectares. And the risk profile that we came to with this property was when we looked at water availability, its risk, it was a very high risk property. As they have no water entitlement, so need to rely entirely on purchasing or trading water when they need it, which is very hard to find willing sellers during dry times. All right, final section of my presentation is on gathering evidence to support enforcement action. So I'll run through a case study, but first, in addition, we share a lot of the challenges that Pablo mentioned that they do in Chile as well. But one additional challenge we face is helping people who need to make decisions about compliance and enforcement, helping them understand the complex nature of this area of work. So I'll show you a GIF if it will play. Let's see. This is something that our team developed to illustrate. Now this only goes for 10 seconds, but the longer version goes on and runs along the channels, turns around the corners to show lawyers and magistrates what it looks like, what the scale of these properties looks like, because it's very hard to get your head around what's actually going on without this. And we found this a very, very powerful visual tool to help explain what we're talking about when we're perhaps in court prosecuting a matter.
Margaret, this is really fascinating, and I'm sorry to interrupt. Do you think you could wrap up in about 2 minutes?
I will, because you're the chair. So yes, I will.
Okay, thank you.
So just in brief, we ran a case study, which was asking us to answer 5 questions about dam construction. The 5 questions I'll just give you was, how much water can each dam hold on this property? How deep are the dams? And are any of them deeper than the natural ground level nearby? Are any of the dams on waterfront land because of the particular rules I mentioned before? When were they built, and how would the water flow naturally over that property if the dams had not been constructed? So I won't, we don't now have time to go through that case study in detail, but suffice to say, we answered all of those questions using technology and integrated with other data. And the results were very pleasing. The great outcome. The court found our technical specialist expert witness credible and consistent, and the evidence compelling. And the court imposed penalties totaling nearly $500,000. That was a very good outcome for us. So, in summary, water as a finite resource under pressure from climate change, population increase, and demand for productive use. It's, as a risk-based regulator, we've got a mandate to be efficient and effective, and so we're using geospatial intelligence and other environmental data to quickly assess risk and identify trends across a very wide and complex area to get a picture of the unseen. And our tech has helped us send field staff to areas of greatest harm, refer high-risk matters for investigation, gather clear and accurate evidence, contribute to defensible enforcement actions, simplify complex information for landholders, the public and the courts. So our eyes in the sky and eyes on the data is a powerful remote sensing and integrated data. And we, in New South Wales, it's transforming the landscape there for monitoring and regulation. And that's all for the benefit of the environment, the communities, and the economy. Thank you. No,
thank you, Margaret. That's great. That a lot to dig in there, and I'm always sorry that I have to interrupt and move on. We've got a couple of questions. I'll take one, and I think hold the other for the larger discussion later. One question specifically for you, Margaret. Can the devices for measuring continuous depths also be used for marine waters, for example, in areas with salmon farming sites?
Yeah, we've been very creative, I think, in the use of our technology for dam depth. And yeah, as I said, we started using castable sounders, which are fish finders, essentially. So there's a lot of, we're finding a lot of synergy between technology that was actually developed for other purposes, or technology that we're not just we're not developing, but we're evolving some of the tech that we've got that can be used for many different things. So yeah, great question. It's a really exciting space, I think.
Perfect. Thank you. Thank you.
Thank you.
So we'll move on to our final speaker. The final speaker is Brittney Flaten, with the New York State Department of Environmental Conservation in the U.S. She is the coordinator of Hudson River Environmental Conditions Observing System. And that by itself tells you this is going to be a pretty tech heavy presentation. Welcome, Brittney, and take it away.
Thank you. It's been really cool to see how other countries are using technology. So this is going to be a very zoomed in discussion of just one river in the US and how New York State is approaching monitoring it. So I hope you can at least take away from this maybe at least a framework that you could try to apply to something that you're interested in monitoring, if anything. But before getting into that, I do want to talk a little bit about the Hudson River and why we are monitoring it so closely. So it's located in New York State, which is on the east coast of the US, and It's just over 500 kilometers long. So it extends up from the Adirondack Mountains and it flows all the way down to New York City. And about halfway through the river, there's a pretty large dam in Troy, New York. And everything downstream of that dam is a tidal estuary. So there's a lot of unique wetland ecosystems along the Hudson. It's home to more than 200 fish species. A lot of them are migratory fish. Some of them are endangered species. And fishing is a huge recreational activity on the Hudson River. There's a lot of tourism around that. The Hudson River also has 5 drinking water treatment plants that source their water from the river, and it serves over 100,000 customers every single day. But there's also more than 100 combined sewer overflow outfalls that dump into the Hudson in periods of wet weather when the wastewater treatment plants can't accommodate all of the inflow. It's also an international shipping channel. It's been home to a number of very large-scale environmental controversies and cleanups over the years. So it's a very dynamic system that has, some competing human and ecological uses going on, which is why monitoring it so closely might be of interest. And so kind of the theory behind the program that I oversee is the idea that if you want to detect some sort of change in a system, you need to first understand its baseline, right? And so that's where the Hudson River Environmental Conditions Observing System comes into play. So the map on the right just has a location of all of our stations. And then I also just have a list of the parameters that we're monitoring there. So they're all pretty basic physical properties of water. The system was formalized in 2008, but some of the stations on this map have been collecting data since the mid-1990s. So it's a very long-term, large data set because data are collected every 15 minutes at all of these locations. So in total, right now, we have 15 water quality stations, and 6 of them have co-located weather stations collecting additional information at that site. So there's a lot of data, and it's all on the web in real time, or I should say near real time. Every hour, the last 4 observations of that hour are uploaded online. And it's sort of unique because it's implemented through a series of partnerships with New York State and other agencies, which I'll get into a little bit. So how it all works. All of the funding for the monitoring program comes from New York State, and that covers the supplies needed to conduct in situ continuous monitoring. So calibration standards, all the equipment that you would need to run everything. It also provides coordination, which is in the form of my role. And then we provide mini grants to our partner organizations. So our partners are all staff who are already embedded at other agencies. So they might have a full-time job working for a federal agency or a nonprofit or a research institution that's interested in the Hudson River, and they get a small stipend to cover their time that they use to calibrate equipment, go out and swap equipment, troubleshoot, and so on. And how we're able to make this all work is that we're all following the same standard protocol. We have a standard operating procedure that everybody follows. We all are using the same equipment, and then everybody gets training, troubleshooting, and tech support provided, mostly from me and some other members of the team that I work with. So I do want to talk a little bit about equipment, but I will have a caveat that, there's a tremendous number of companies that produce equipment that can do the kinds of monitoring that I'm discussing. So just because we use it doesn't mean you have to. This is not some sort of endorsement by any means, but I wanted to provide a sort of simplified framework of how this works. So we have a multi-parameter sonde, which is measuring water quality parameters. That's just located in situ in the river all the time. And then roughly every month to up to like 90 days, someone is going out and replacing that equipment with something that's been freshly calibrated. Then you might also have weather equipment on site, and both of those are tied into a data logger. You might also hear it called a data collection platform. There's a variety of ones out there that you can purchase, but really what it's doing is taking information from separate sensors and collating them in one place. And generally you can, get those in the form of a comma separated file or an Excel file to actually work with the data. We use cellular modems to provide connectivity from our remote locations to our servers and our software that we have. And what's nice about cell modems is that you can communicate both ways. The station can communicate with you, and you can actually communicate with the station if you need to. There are some other agencies in the US that use satellites to provide their remote connectivity, but you can't communicate with the station. The station can only communicate with you. So there's some drawbacks to that. I want to get a little bit into software and the framework that we use, because our data are serving multiple purposes at once. For example, we want people to be able to go online and see the water temperature at the park that they like to fish at in near real time. But we also want to be able to collect a long-term continuous data set that can be used to bolster research projects or inform resource managers. And so it's kind of hard to fulfill both those purposes at once. But the first thing, the real-time data, we have raw field data that gets automatically filtered by some software that we have. And I'll get a little bit more into what that's looking at on the next slide. But then it produces a data stream that anyone can view in real time online. In parallel to that process, though, the filtered data get put into a provisional database. And then on a quarterly basis, roughly, that gets reviewed by actual people, not just software. And then that produces the final data set. And because of the nature of how we are funded and how we collect all this information, it's all available for free to download online. So I want to talk a little bit more about data review and how it can fulfill kind of two purposes at once. So that first top part of this previous slide is really what I call primary quality control. And it's done by some custom software that we have. And it's really looking for obvious mistakes, because we don't want equipment malfunctions or some other issue to show up to the public, right? So it's checking for things like if the data we are getting are within the range of the sensor. For example, the pH scale only goes to 14. So if we're seeing a pH of 72, there's clearly some sort of issue with the equipment. And so that value should be hidden from public view. And then on the back end, we receive a notification that there's some sort of issue at the station that needs to be addressed. We can also implement stricter tests because we have the ability to add whatever tests we want on the front end. So we also do some seasonal range tests, basically looking at something like water temperature in January shouldn't be 25 degrees Celsius. That's clearly a problem, and that should be hidden from public view. For context, for people who don't live here, it's very cold here in January. Usually the water temperature is about 1 degree Celsius. And then the second part, which we still use people to do, is the secondary quality control. And this is to help clean up that data set and make sure that it's as high quality as possible. And so because there's people who are physically going to these sites, retrieving the equipment, replacing it with new equipment, and so on. They're very familiar with the conditions at their site, and they're also very familiar with their equipment and if something happened to it, in the month or two that they had it deployed. So that can provide really important context that, software might not pick up on. Then we can use Excel macros or R scripts and have it look for more specific problems. For example, there might be sudden spikes in a parameter, like turbidity or water clarity, for example. And it's up to a person to decide whether or not that's anomalous, an error, is it representative of real conditions, or did something happen to the equipment? So that's part of why we have those co-located weather stations, because something like rainfall data might inform whether or not spikes in turbidity are representative of real conditions, like a sediment plume after a rainstorm, or if there was some sort of malfunction. And then we also like to make sure that the software that was filtering things automatically didn't make any mistakes, so that's why we have someone look it over. I want to talk a little bit about some pilot projects that we're working on, because that might be of interest. So we are looking into monitoring for chlorophyll and phycocyanin, which is an accessory pigment of cyanobacteria, because there are sensors available on the market that can, detect those pigments in the water. And those are both important indicators of an algal bloom. And we actually had a very severe algal bloom in the Hudson this summer. It was basically the most intense one of anyone's recent memory. And it was, confirmed to have harmful bacteria that, made it unsafe for people to go in the river. But a lot of these sensors provide sort of relative measurements. And so what we want to do is pair with grab sampling. So going out to the site and also collecting a physical water sample, because you can then build a relationship for your specific site based on the grab sample and what your instrument is measuring. We're also interested in pairing this with remote sensing data, because you can detect these algal blooms from space. And so we're interested in looking at what point are our instruments detecting that there's a problem, and at what point can you see that, on imagery? And is there some way that we could model that relationship? Another project that's been ongoing with the United States Geological Survey is they are working on tracking the estuary salt front. So like I mentioned earlier, the Hudson is a tidal estuary, and the location of the salt front, which is where the transition between fresh and salt water happens, is very dynamic. It moves all the time based on the tide and also based on the season and the amount of fresh water coming from upstream and pushing that salt water back out to sea. And because we have drinking water plants located on the Hudson, knowing where this salt front is very important, because it needs to be far away from those drinking water treatment plant intakes. And because we are collecting continuous in situ data all the way from New York City up to Albany, which is just below that dam in the estuary, we can use our data to validate and test this model that they're developing, which is exciting. And then the last thing that I am hoping to implement next year is sort of a warning system, which I think some of the other folks here described a little bit. And basically, it would be a way to have users choose a location and a parameter and a threshold that they're concerned about, and you would get automatic emails when that threshold was, exceeded. So an example might be, if I knew someone at the drinking water treatment plant, maybe they want to set up an alert system when a station nearby begins to experience an increase in conductance or salinity. So those are some things that we're working on right now. I also want to talk about some other use cases for this kind of tech that I'm, not currently using, but it is out there and could be used in sort of enforcement and compliance context. So there are a lot of other sensors on the market that can detect nitrogen-based compounds, fluorescent dissolved organic matter. You can also monitor in light water conditions, and there's also some sensors that have the capability to do dye tracing, all of which might be of interest to some folks in this group. And you could see how that could very easily fit into this framework that I've already described. Lastly, I just want to talk about some considerations. Whether or not you want my advice, I will give it. So I guess the first thing to think about in terms of data collection is if you want data or if you want it in real time, because there are a lot more things that you have to invest in if you do want real-time data. Particularly from remote areas, you're going to need things like solar panels and a strong cell or satellite signal to get that information back to your office. There's a lot of technology that you can just deploy and retrieve later and get the data off of it. But if you want to see it from your desktop, it's a little bit different. Then another, barrier perhaps is that once you determine what you need, frequently things might not be compatible out of the box. A lot of different companies have proprietary cables or signals that don't talk to each other. So you really need to, work with them to figure out if you're able to do what you'd like to do with the product that you're interested in. Another, concern with in situ monitoring that, is a big downside is that you're only able to locate equipment where you have permission to do so. So here in New York State, most of our stations are located at property that's either owned by a nonprofit or a university who are interested in monitoring, or maybe it's at a public park. Whereas, if we want to be near something that is, a potential polluter, you might not have the ability to do that. And then something that I run into a lot in my work is just sort of the hesitancy to adopt more advanced technology. There's a lot of concern about risk around machine learning and a lot of concern about, security basically and privacy. So you have to kind of take that into account doing this kind of work. And then the last thing that, we run up against sometimes is the idea of having open source data versus not. We have to have all of our data be publicly available, and anyone may use them for whatever purposes, though they are asked to give, appropriate credit. Whereas, in other contexts, there might be legal or privacy reasons that you cannot share the information. But for us, that's not really a problem. Everything that we're collecting is pretty standard, dissolved oxygen temperature. Everyone has the ability to know what that is. I also just wanted to give a highlight to some other programs because there's a lot of other agencies that do work on the Hudson. And I kind of wanted to summarize some of them here, and there's, links to their various websites. So Riverkeeper is a nonprofit that works on the Hudson River, and a lot of the water data that they collect are specifically in the context of human use of the river. So boating, swimming, fishing. And so they do a lot of bacteria monitoring and then also just general physical characteristics of the water. The United States Geological Survey is a federal agency that they have a lot of work going on the Hudson, and they're a partner of ours. The Hudson River Estuary Ports Network is part of NOAA, which is another federal agency. They specifically provide tide, water level, and navigational safety information, mostly in real time, which is important since the Hudson is a shipping channel. And then one sort of cool program that I wanted to highlight is the Hudson River Ecosystem Monitoring Project. Because there's been a lot of environmental damage to the Hudson over the years, there is a lot of settlement money. And so that can be used to fund research and identify, gaps in research that need to be addressed on the Hudson. So there's some cool research projects that have come out of that. So at this point, I'll take questions. I know that was quick.
Great. Thank you, Brittney, and your timing was perfect. There are a couple of questions from you in the Q&A that are somewhat technical from your neighboring state of Maine, and I'm thinking perhaps you can respond to that directly.
Okay.
And we
Yeah.
can then move ahead to our more overarching conversation here that will involve all of the panelists. So I invite all the panelists to jump in here. And we've got a number of questions that have popped up in the chat. There are some others that I've received from the panel. I'd like to start with one question that was asked in the Q&A, and I think the speaker that it was directed to answered it, but I wanted to go back to it because it's kind of the bottom line question, and I don't have the exact wording anymore, but I think the question was really about the overall value case for using advanced monitoring compared to traditional inspections and company reporting. And this is from the perspective of how do you persuade agencies that have limited budgets that this is a good use of their resources? Do you see a net benefit to shifting to more advanced monitoring? What's that overall value case? And I'll throw this out to anybody who wants to take a shot at that.
Well, I think you mentioned that agencies, might be short of money. It's exactly answering that from our perspective. It's really about directing the effort where it needs to go. So using technology to do the broad scan, to do the quick work, to do the analysis perhaps that humans aren't so quick or good at, to point people in the right direction. So focus on the things that really matter rather than humans trying to manually do everything. So for us, we've found the argument has been very compelling around focusing our attention on the high risk issues, because we can't do everything everywhere all at once.
Thank you. Thank you. Does anyone else want to offer an opinion on the overall picture of using advanced monitoring versus the more traditional methods?
Yeah, well, I guess I'll have to agree with Margaret because in her case it's the same. Of course, there might be some lines of work that probably will require some initial investment, but at least like the marginal cost of all of these tools and all of these actions is I mean, it's not zero, but it tends to zero. And again, I don't know if you said like the comparison is like one or another or the other, but like the combination of both. And given that, of course, we have very limited resources for like enforcing on sites, I guess like the question for us at least is like, what's the optimal combination of these two, like, if you want to say like two categories of actions?
Great, thank you. Anabela or Brittney, you want to take that on?
Oh, I tend
Got
to
a
agree
30-second elevator speech. How do you persuade someone that this is a good way to go?
Well, I tend to agree with Pablo. Well, in EU, we also we are trying to use this kind of new advanced methodologies, namely for quantitative assessment, so for water quantity, and namely for example, for groundwater. We have some projects, and we are dealing with. So we are the problem is we are dealing with the how can I say the credibility of the data, because for groundwaters, the geology interferes a lot. So we are now researching and we're trying to implement it. And we are with Impel network, we are trying to more European at European level, try to define common standards for the use of these kind of methodologies. Yeah.
Great. Great. Thank you. Well, that leads into another question that I think has been touched on in a couple of the presentations, but does data from new types of devices that looks totally different from the data that has typically been used in the past for enforcement, does it present challenges in terms of being used as evidence in court? Is there work that needs to be done to make that step?
Oh, well, I'll jump in again. This is, this is exactly, I showed that brief GIF that we had developed. This is definitely an area that we have had to work hard, and it's not just about new data, but it's about data to a new audience almost. So it can be, even pretty basic technology. When we're prosecuting a case in a local court in New South Wales, you've got magistrates who are dealing with very, very different issues. They're not dealing with water theft or controlled activities on waterfront land. They're dealing with many, many other things. And so this will be a one-off in many cases. And so the level of education that's required around bringing up that to a basic level, that knowledge is quite significant. So, and it gets, so the more complex or the newer the data, I think, the harder that challenge becomes. We've introduced an education and engagement arm in part to help us educate the legal community, just one stakeholder of many.
Thank you. Anyone else have thoughts on how to use this data in court?
Well, ensuring the quality of the data and ensuring the data has collect the evidence is something very complex, and and we need to ensure that the data so we have to demonstrate that all the collection of the data and the treatment of the data secured and it's credible for enforcement. So in that case, education, yes, it's and for that, for example, under at European level, the 4 networks. So the Impel, which is the implementing and enforcing network, the NPE, the prosecutors network, the NFJU, the judge network, and also the police network. So we try to collaborate and to try to work together, namely to show how can we use this kind of new technologies, new assessment of data, because it's not only the new technologies on monitoring, but also the new technologies, namely AI, on treating the data. So that's another area, and it's something that we also we are starting also to work it, and we have to demonstrate that in the end the data indeed that is collected demonstrates what is happening in field. So, and a lot of work needs to be done, like Margaret was saying, as a judge is judging like some robberies or some domestic violence, and then it goes to a judgment of water thief or water pollution. It's something that they are not ready. So we have to collaborate more to show that indeed, because environmental crimes are just the 4th type of crime, more in terms of profit worldwide. So it's a new challenge, and it's not easy, but it's possible. Yeah, that's my thoughts.
Thank you. Ending on a high point. That's good. You'd mentioned using AI, and this overlaps a little bit with one of the considerations in Brittney's slides about machine learning. So I'm actually making this up. I'm not sure exactly what the question is, but I guess the question is, how do you see machine learning being used to take advantage of this really a flood of all kinds of data that we haven't had before? What are the opportunities that presents? Use of AI, I guess, is parallel to that. So I guess what are the opportunities, and then also what might the challenges be of trying to use that kind of data analytics? So what are the pluses and minuses of that kind of advanced data analytical work?
I guess I could start. I think it's a tremendous opportunity. But at least from like a state government perspective, I would say the chances of it being adopted by our agency is probably almost zero. We get all sorts of mandates that we're not supposed to interact with any sort of AI tools. Like Google Chrome just updated and has the Gemini thing right at the top. And if you try to click on it on your state computer, you get all these pop-up windows that come up. So I think our agency is very skeptical of like the security and privacy risks of AI. And so I think trying to explain how to use it in like a science context would be difficult just because it's such like a buzzword that concerns, I think, leadership.
Hmm.
Yeah.
What do other people think? Is it a plus or a minus?
Yeah. What Brittney mentioned it's a very important issue for federal agencies or state agencies in this case. But I mean, if AI today or machine learning a couple of years ago, I guess that the plus is the main strength of that tools is like finding patterns. So I see, for example, with these streams of data that we receive, I see an opportunity of AI or machine learning methods for helping us, right, to find patterns with all the caveats that Brittney mentioned, like especially with AI, like how we keep sensitive data or strategic data secure. But risk, I think there's plenty of risk. One, for example, is, well, I guess like overconfidence and in eventual imperfect data. Like if we don't have like good quality assurance processes for the data, we might be taking wrong decisions. Like we can have like a very fancy model, like AI model, but if it's not grounded on like very good data, then right, models can be wrong, right? I think one thing is that, and also like not to confuse data with like judgment. Like we need to have a human always revising and actually making the last decision. I guess that's central for at least for agencies that enforce. So again, I guess there's a lot of opportunities, a lot of pros, but given that we have like these checks, right, of data, confidentiality, transparency, and so on.
Great. Thank you, Pablo. We've got a question from the audience, closely following on my question about evidence in courts, asking all of you if your jurisdictions have specialized environmental courts, which might be able to understand the complexity of data and other technologically obtained evidence, or are you? The examples a couple gave, or are you just dealing with courts of general jurisdiction who, as someone said, move from domestic violence to a complicated environmental case? Is anyone dealing with a specialized environmental court?
Yes, we do. We have the Land and Environment Court in New South Wales. So we do take matters to the LEC, but it will be a case-by-case basis, and we'll make that decision relatively early. Very significant big, high profile, etc., we would typically take to the Land and Environment Court. But there is, we've also got civil penalties available to us as well. So there are reasons we would go local court, and in fact, you can end up for you can end up with a reasonably significant penalty awarded through the civil process as well, that you don't have available in the Land and Environment Court. So yes, you've got the advantage of the knowledge and the experience and so forth, but there are some limitations, I suppose, for us. But yeah, we're lucky. There's a Land and Environment Court available to us.
Does anyone else have a specialized? Go ahead, Pablo.
Yeah, we also have environmental courts here in Chile. We have three, which are separated by region: one in the north, one in the center, and one in the south. So right, that of course helps to manage these cases, but still, I guess that there's still challenges as the one we were discussing before. We still have to sometimes, if there's a new method, a new technology, a new data source, try to explain like how that new data might be comparable to what we have used before, or how a number is produced, or right, clearly explain the methods that has been said before. But of course, that's having these environmental courts helps to process this kind of new or complex data that we have in environmental settings.
Thank you. Go ahead.
We don't have a specialized environmental courts, but in Portugal, so we work together. We've been working together with the prosecutors, namely in developing the best ways to assess data, for example, to define water damage in case of pollution, for example. And we have a national network, so we call it National Impel Network, where we are the environment agency, environmental inspectors, the environmental policies, and also the prosecutors and the judges. So the court decided to become as another observer to learn, so to understand a little bit more, to deepen their knowledge on environmental issues. So it's a step by step. We are going there.
Yeah, that's interesting. So you have a vehicle that you can use to do some background education outside of the actual cases. Is that sounded like that's what you were saying? Yeah. Okay.
Exactly.
Yeah. Well, we're getting pretty close to the end. So one question that came in to me in advance from the panel might be a good one to end on. If a regulator is just starting with advanced water monitoring, what would you suggest as first steps? And it obviously depends on what problem you're trying to work on, whether it's water scarcity, water pollution, and so on. But any thoughts on, for those who are just getting started on this?
Yeah, I'll go. Yeah, I guess in our case, a good approach when we started working with this kind of data and approaches is to build like these multidisciplinary teams. Like, so we have the data folks, the IT folks, like the very technical in that sense folks, but it's very important to work with the water specialists, for example, that we have here in SMA in particular. So the best cases, not only for water, but in all other cases we have built, the best example of like real and impactful action we have had, even when using maybe not very like complex models or data, but using data and technology, have been these that have been co-created with the teams and like revised and built together. I'll say that's the main takeaway from all the years we have been working on these issues.
Great, thanks.
And I would say develop a proof of concept. So start small, don't try to boil the ocean. Like start with a finite, problem or challenge or whatever, and really build it up from there. That's where you get good buy-in, in our experience.
Thanks. Thanks.
I think you could maybe do, I agree with everything that's been said so far, but you could also maybe sort of investigate what data already exist and maybe see if there's a way that you could leverage existing data sets and then identify, how your agency or group could fill in perhaps the gaps to make something work for your purposes.
Right, so they build on what you've got.
Yeah.
Well, thank you, everyone. This was a really rich conversation, both the presentations and the discussion. Thank you for your time. I'm going to hand it back to our convener, Susanna.
Great. Thanks so much, George. And thanks to all of our speakers, Pablo, Brittney, Anabela, and Margaret, for an engaging discussion. And thanks to our audience for the questions. If you joined late or couldn't attend the full webinar today, you'll be able to watch the recording on the event webpage at eli.org within a few business days, and everyone's slides will be there as well. There you can also find our calendar of future events, and we hope you'll join us again. So thank you, everyone, and have a great rest of your day.